And now to finish out Chapter 3, we're looking at Section 3.6 on relative velocity. Our goal here is to define what relative velocity actually means and be able to apply this to some motion problems. In the first week of class, we discussed the need for a fixed reference point, basically your origin of a coordinate system where you are going to define position relative to. From that spot, we can define position r, velocity v, acceleration a. Everything is defined relative to that particular point. Basically, this section looks at what happens when you might have a reference point that is also on the move. So let's say that two observers are observing the same thing. Let's say that in this car over here is Mrs. Wright, and she's driving down Highway 50 at 60 miles per hour. And two observers of Mrs. Wright, one of them will be maybe Mr. Wright in this car over here. He's also driving down Highway 50 at 60 miles per hour. And the other one is you over here, saying, hey, there goes my physics teacher. So each of you are observing Mrs. Wright driving at 60 miles per hour, but each person is going to define the velocity of Mrs. Wright differently. According to you, who's standing over here on the side of the road, you see Mrs. Wright flying by at 60 miles per hour. You would say that my velocity is 60 miles per hour in whatever direction it is I'm traveling. On the other hand, if you were Mr. Wright in this car over here and observing me, to Mr. Wright, it looks like I'm just sitting right next to him because he's also moving at 60 miles per hour. It doesn't look like I'm moving at all. It seems like I'm just staying stationary. So he would define my velocity to be 0 miles per hour. Essentially what we're seeing is that to Mr. Wright, we would take the speed that I'm moving at according to you, or a stationary observer, and subtract the speed that he was moving at to find the velocity that it looked like I was moving according to him. So each observer would define that motion differently depending on where they were viewing the motion from. Now let's look at an example of a relative velocity problem. Let's say you have a boat that's heading due north across a wide river, and the boat is able to travel at a speed of 10 kilometers per hour. The river is going to have a current so that the water moves with a uniform speed of 5 kilometers per hour due east. And the question is, what is the velocity of the boat relative to the dock? Now, as we look at this, if we have the boat heading directly north across the river towards that dock, and yet we have the current, we know that the boat is realistically going to be moving in a direction more like this. So you can see that we get this very nice right triangle where we could find the value of this object's velocity moving in this direction by using the Pythagorean theorem. So the velocity of the boat relative to the dock can be set up in a Pythagorean theorem and solve for. If you'd like to pause the video for a second and solve, go ahead and do that. You should find that the velocity of the boat relative to the dock is going to come out to be about 11.2 kilometers per hour. So this value here is 11.2. We could also find the angle or the direction that the boat is heading because, again, velocity is not just how fast, but it's also a direction as well. And we could find that value by setting up a tangent function, where the tangent of that angle theta that we're looking for is going to be equal to the opposite, or the 5 kilometers per hour, over the adjacent, or the 10 kilometers per hour. Solving that, you'd find that theta is equal to about 26.6 degrees. Now, another question we could ask ourselves is, what direction would this boat have to head so that it actually ends up moving directly across the river to the dock? Now, if we set up this same problem again, and let's just maybe put it over here. So here's the dock again. And the boat is now going to be heading in a direction so that it in fact ends up moving directly across the river. So the boat would have to be pointed, maybe something like this in order to work against that current that's pushing it towards the east. In this case, we want the boat to actually end up moving directly across the river to the dock. We still have that current of 5 kilometers per hour, so we need to keep that in mind. And we know that the boat is able to move at 10 kilometers per hour. Now, if you were asked what direction the boat might need to head in order to actually get directly across the river, you might initially think that it's going to be the same angle that we found over here in this other problem. But if we look carefully at these triangles, we'd find that they are not, in fact, the exact same triangle. We still have the 5 across this side here, just like we did on the other side. But what you'll notice is that the 10 has now become the hypotenuse rather than one of the legs of the triangle, meaning that this triangle is not the exact same thing. So when we attempt to solve for our theta, we can still use a little bit of trig to solve for that. In fact, this time we may want to use a sine function because the sine of the angle theta is going to be equal to the opposite over the hypotenuse. So when we actually solve for theta, we'd find that the angle that you should be heading is about 30 degrees. And that would be from the north direction, about 30 degrees west of that. We could also find how fast you would actually end up moving across the river to move directly north, again by setting up a Pythagorean theorem where the velocity of the boat would be found by taking the square root of our 10 squared minus the 5 squared. And you'd find in this case that that velocity would end up being about 8.66 kilometers per hour. So hopefully this helps you get a feel for relative velocity, what it means, and some sample problems that you might see related to it.